Similar, more practical sort of question is, once we make enantiomers, how can we separate them? And so a resolution is a process that does this. It creates, it's a separation method for enantiomers. So resolution is a separation of a racemic mixture into its respective enantiomers. The process for doing this is actually very similar to what we just talked about with creating chiral centers. Enantiomers are identical, and so what we must first do is we must first convert them into diastereomers, because then and only then will they have different energies. Once we create diastereomers, they will be easy to separate, and so then we can then convert them back into their single enantiomers by doing some simple chemistry. So the classic example of this is using some acid-base chemistry to separate molecules. So let's say we have this racemic mixture. Let's say we have a racemic mixture of this chiral amine. Okay, we know that this amine here has a stereocenter, and it has an RS configuration at that stereocenter, and so this is a racemate. Okay, so let's say we take that racemic mixture, and we know that this racemic mixture is a mixture of both the plus and the minus, or the R and the S enantiomers. So here we go. We've got at this position an R stereocenter or an S stereocenter. Right, so that's what this molecule is. So let's take this racemic mixture and let's treat it with a carboxylic acid that is chiral. In this particular reaction, the reason we do this is because there's an acid-base reaction that occurs. So this chiral center here is really our resolving agent. This is what allows us to create diastereomers, and you'll see this in a second. But really the acid-base chemistry comes from the fact that that proton there is quite acidic, and because we have, in the case of the chiral amines, or the racemic amine, the nitrogen on that on those R and S enantiomers are quite basic. And so what we can do is we can protonate each of those amines, and then we create a diastereomeric salt. And so let's show that right now. So let's say that first amine, the R amine, grabs a proton. It becomes NH3 plus. And then the anion will be O minus, but it will still retain the chirality of our resolving agent. And let's say our resolving agent has a stereochemistry at that alcohol of S. So this is S, and this is still R. So we're going to call this this salt here, it's kind of like having sodium plus and chloride minus. It's a contact ion pair. You can treat it as a regular sort of inorganic substance. We call this the RS diastereomer. But what we also have is the SS diastereomer. So the SS diastereomer will be the other chirality at that center. So this is now the S. And again, we have the same counter ion, this chiral alcohol, which was our resolving agent. So again, this is the SS diastereomer. Now these diastereomers can behave as one molecule. So this whole thing here is one molecule, and this whole thing here is one molecule. They happen to be diastereomers. And so because they're diastereomers, they have different physical properties. So what we can do is we can take these diastereomers and we can separate them. And so we separate them by a process known as differential crystallization. They have different properties, which means they have different solubilities in organic solvent. It is likely that one of the diastereomers will be much more soluble than the other. And so what we can do is we can filter off the insoluble diastereomer, leaving the soluble one behind. And so this happens sort of arbitrarily. Let's say that let's say the SS diastereomer happens to be more insoluble in organic solvent, and so now we have a method of separating physically one of the diastereomers from the other. So now we have this SS diastereomer. Here's S, S. So I'll just say here filtration. And what we're left with is the other diastereomer, the RS, will still be completely soluble. So here's R, S. And then at the next stage, what we do is we don't want the diastereomers. We actually wanted to separate our racemic mixture into its respective enantiomers. So we need to recover each of those enantiomers now. So what we can do is we can add a base. Any base will work. So B with two electrons. Maybe, for example, if you wanted an actual ion, let's say hydroxide would do the trick, or bicarbonate would do the trick. So you generate, in this case, a deprotonation event. You remove the proton from the ammonium ion, part of that diastereomer. And what you're going to get is now the new amine. And this new amine will be a single stereoisomer. This will be soluble in organic solvent. And then you'll have other things that are water-soluble impurities. And those, of course, can be filtered away. Same thing can happen to the other diastereomeric salt. We can take OH again, and we generate then the free amine. But this time that free amine has the R configuration. Again, soluble in organic solvent, plus the water-soluble impurities. You can separate those out. And so now you have your R enantiomer and your S enantiomer completely separated. 50% of your R enantiomer, or 50% of your racemic mixture is now the R, separated from the 50% of your racemic mixture, which is the S. Now let's say you just wanted the S enantiomer. This is an inherently wasteful procedure because then you wouldn't use the 50% of your material. 50% of your material is the R enantiomer, and that would just be waste. And so this is a big problem in organic chemistry, is trying to generate single enantiomers without having wasteful procedures in which you just throw away the other enantiomer. There are other types of resolutions. This is a resolution in which you take advantage of this differential solubility, differential crystallization. This provides a mean of sort of physical separation of those two species. But there are other types of resolutions that you can perform. These are enzymatic resolutions where an enzyme preferentially binds to one enantiomer and performs a chemical reaction on it. And another example would be chiral chromatography, where you have selective adhesion of one enantiomer to a chiral stationary phase, and this also allows separation of isomers. The general principle here is that you're taking a racemic mixture and you're creating diastereomers out of that racemic mixture, and then those diastereomers have different properties.